A 5 nanofarad parallel plate capacitor is charged to 160 volts. It is then disconnected from the battery and immersed in distilled water that has a dielectric constant of 80. What are A, the capacitance and voltage of the water-filled capacitor, and B, the energy stored in the capacitor before and after its immersion? It's, as usual, worth drawing a picture or diagram so that we can understand what is happening here. So I'll draw the parallel plate capacitor as usual. So here's one plate, and here's the other plate. We imagine that things start in vacuum. So in vacuum, there's nothing in between the plates, which we imagine have somehow been charged up to have a bunch of, let's say, positive charge on one side and a bunch of negative charge on the other side, and the electric field points from the positive to the negative side, something like this. Electric field on the inside, there's a charge Q and a charge minus Q, and there's some amount of potential energy stored in the capacitor. Technically, it's stored in the electric field itself. Now, initially, there's a potential difference, 160 volts, between one side of the capacitor and the other. And then what happens is it's disconnected and submerged into a liquid. Distilled water is the liquid. And let's go ahead and have a sense of what that might look like. So there is still electric field on the inside, but there's also, I'm going to color it in green water. This is the dielectric that has a value of kappa equal to 80, whereas over here, the vacuum, where kappa is by definition equal to 1. Now what should happen is that the amount of charge stored on each plate should remain constant. What will change, however, is the amount of voltage across the capacitor as measured between these 2 points. We know that there's a sort of master equation that's at work here, which is that the capacitance is equal to the amount of charge stored divided by the voltage across the capacitor. We can use that. At some point, we may also need to use the fact that we've got a parallel plate capacitor, and the formula for that, the capacitance of a parallel plate situation, involves epsilon naught times the area divided by the plate separation with the dielectric constant sitting out front. That's important to realize that the value of kappa is variable. At least we'll have two different scenarios here. So I'm going to color this in green. We also at some point might need to know about the energy stored in the capacitor. The potential energy stored in the capacitor is given by 1/2 times the charge stored times the voltage across the capacitor. And this can also be written in other ways, like 1/2 times Q squared over C, or 1/2 C times V squared. Okay, so in part A, we're supposed to figure out what is the capacitance and voltage of the water-filled capacitor. Well, I suppose what we can do is borrow the result above, that the capacitance of the parallel plate is given by the dielectric constant times epsilon naught A over D. In other words, it's multiplied by the capacitance in vacuum. The capacitance in vacuum is really the answer that we're starting with. And so what I would suggest is at this point, we can stick in the numbers that we have. The dielectric constant has a value of 80. The vacuum capacitance is the value that is given to us. That's 5 nanofarads. 80 times 5 is 400, and so I would suggest that the capacitance here is 500 nanofarads. In other words, it's increased by a factor given by the dielectric constant. Now, what is the voltage of the capacitor when it's immersed in this liquid? Now, the voltage, realize that we can rearrange one of these equations, this one for example, and write the voltage as being equal to the amount of charge divided by the capacitance. The amount of charge is fixed. What does change is the capacitance. So I'm going to go ahead and write this as the capacitance being equal to the dielectric constant times the vacuum capacitance. Now, one more thing to say here is that we could plug in relevant numbers here, but it may in fact be easier to recognize that Q over C naught, that would be equal to the original voltage, V naught. So probably the best way to think about this is equal to the original voltage of 160 volts and then divided by the new dielectric constant, which is 80. 160 divided by 80 gives you 2 volts. All that is to say is that if you increase the capacitance of a capacitor, then the amount of voltage required to give you a certain charge is less. So that is consistent with our expectations. Now in part B, the energy stored in the capacitor before and after its immersion. So we're going to use this formula or one of those formulas to determine this. At the very beginning, we are given the value of the voltage and the capacitance, and so it's probably worth using the formula 1/2 C V squared. So let's go ahead and do that. Before, if you like, in vacuum, the energy stored in the capacitor would be given by 1/2 times the original capacitance times the original voltage. And so that is 1/2, original capacitance we're told is 5 nanofarads, 5 times 10 to the minus 9 farads, times what the quantity is, 160 volts, and square that. Multiply everything and you'll determine that this is 6.4 times 10 to the minus 5 joules. You can also write that as 64 microjoules if you want. After, what should the expectation be? Well, the dielectric does something to do with the energy. The dielectric makes it possible to store more energy, so you might expect the energy to go up. So go ahead and we'll write the energy afterwards as equal to, it's the new capacitance times the new voltage. Keeping in mind what we found before, that the new capacitance is given by the dielectric constant times the old capacitance. The new voltage is given by the old voltage divided by the dielectric constant. And since that part is squared, overall, this is going to be equal to the original energy, which I'll call U naught, divided by the dielectric constant, 1 power of dielectric constant. And so what this means is this amount is equal to 6.4 times 10 to the minus 5 joules divided by a factor of 80. And what we get when we compute this is equal to 8 times 10 to the minus 7 joules. So in fact, the potential energy stored in the capacitor has gone down.